Welcome to The Explainer. I am so thrilled you're tuning in today because we're going to tackle a concept that's literally the bedrock of modern artificial intelligence. If you're diving into linear algebra to figure out how large language models actually tick under the hood, you are in the exact right place. Today, it's all about vector norms and magnitude. Basically, this is the critical math that makes AI similarity search, recommendation engines, and word embeddings actually function. Honestly, without this mathematical foundation, the AI models we use every single day would just be completely lost in a sea of numbers. So let's get ready to build a really deep visual understanding of how AI measures the exact size of a vector. To kick things off, I want you to picture something. Imagine two vectors drawn on a grid. They're pointing in the exact same direction, totally parallel to each other. But one is kind of short, and the other stretches way, way further out. Are they the same vector? Well, the answer is a resounding no. Up until now in your linear algebra journey, we've talked about vectors purely as arrows, right? We've added them, we've subtracted them, multiplied them with the dot product. We know vectors represent those direction and length. But we haven't answered the most basic, fundamental question you'd ask about any arrow you see in the physical world. Precisely, how long is it? Figuring out how to measure a vector's most basic property, its length, is the whole shebang for our explainer today. And that brings us straight to our core definition. Vector norm is really just the formal mathematical term for the length or the magnitude of a vector. That is literally all it is. There's no complex trickery here. Now, look at that little V surrounded by the double vertical bars. Those bars are the universal symbol for the norm. Actually, a quick heads up, they are not absolute value signs, even though they look a bit similar. When you see those double vertical bars around a vector in an AI research paper, it's essentially a command. The math is telling you, hey, strip away the direction of this vector and purely isolate how far it goes. It isolates the size. To kind of ground this abstract math in reality, let's look at a concrete, real-world analogy. Think of your house as the origin on a map, coordinate 0, 0. Your office is out there somewhere on the city grid. The vector from your home to your office captures the direction you have to travel and how far you have to go. The norm? The norm is simply that second part, the absolute straight line distance. Not the winding roads you drive, not the left and right turns, just the distance as the crow flies. Or if you picture an actual arrow shot from a bow into a field, the norm is literally how far that arrow traveled from the launch point to the landing spot in a perfectly straight line. Distance from the origin. It's really that simple. Okay, section 1, the L2 Euclidean norm, the Pythagorean theorem in disguise. Let's jump in. So do you remember learning a squared plus b squared equals c squared for right triangles back in geometry? Well, we use that exact same idea right here. Let's walk through it using a simple two-dimensional vector that stops at the coordinates 3 and 4. If you draw this on a grid, you naturally form a right triangle where the horizontal leg is 3 and the vertical leg is 4. To find the length of the vector itself, which is just our hypotenuse, we follow 3 easy steps. Step 1, we square each component, so 3 squared is 9 and 4 squared is 16. Step 2, we add those together. 9 plus 16 gives us a sum of 25. And finally, step 3, we simply take the square root of that sum, which gives us a clean, perfect 5. 5 units. Boom. That is the final calculated magnitude for our example vector. It is for sure that straightforward to find a vector's exact length. But of course, in artificial intelligence, we aren't just playing around in 2 dimensions. We're working with language embeddings that can have 300 or even over 1,000 dimensions. The beautiful thing about linear algebra, and this is absolutely crucial, is that this exact same Euclidean formula scales effortlessly, whether it's 2 dimensions or 1,000. The rule never, ever changes. You just square every single component, add them all up into one massive sum, and take the square root. That single resulting number is the exact magnitude of your massive AI vector. Moving on to section 2, the vector norm family, beyond the Euclidean distance. Now, the L2 norm we just walked through is actually just one member of a much larger family of equations called the LP norm. By changing the value of p, you actually change how you measure distance. We have our familiar L2 norm, the Euclidean straight diagonal line we just did, but then we have the L1 norm, which is often called the Manhattan distance. Think of the L1 norm like walking city blocks in an urban grid. You can't just cut diagonally through skyscrapers. You have to go right and then up, forming an L-shaped path by just adding the absolute values together. And finally, consider the L infinity norm, also known as the max norm. This one ignores the grid entirely and simply hunts for the single largest component in the vector, ignoring all the rest. While L2 is definitely the star of the show for embeddings, you're going to see L1 and L infinity pop up constantly in machine learning optimization. All right, section 3, normalizing vectors for AI, stripping away size. Let's see why this matters. So, why does any of this matter for a language model? Well, imagine you have two word embeddings, vectors that represent words. They point in almost the exact same direction, meaning the AI thinks they represent very similar concepts. But one vector has massive numerical values, and the other is tiny. If you compare those raw embeddings, the huge vector will absolutely dominate the math. The similarity calculation gets heavily skewed, not because the words are actually more similar in meaning, but purely because the raw numbers are bigger. It's totally misleading. And that is exactly why AI systems create normalized vectors. Before comparing them, the system divides every vector by its own calculated norm. By doing this, we strip the size away entirely. We put all vectors on an equal footing, isolating only their direction. So the crucial point here is the number 1. When you take a vector and divide it by its own norm, you shrink it or stretch it so that its new length is exactly 1. We call this a unit vector. If every single vector in your AI system has a length of exactly 1, size is completely removed from the equation. The playing field is perfectly leveled. And you know, that normalization step is the absolute foundation for so many crucial AI techniques. First off, it sets up cosine similarity, which we use to compare the actual meaning of words or sentences. It's also used in regularization, where L1 and L2 norms keep a model's weights from growing too large and just memorizing the training data instead of actually learning. Plus, it's used in gradient clipping, which caps the magnitude of gradients so the AI's learning process doesn't become mathematically unstable and just blow up. So whether you're capping gradients or comparing human concepts, it all starts by measuring and then controlling the vector's size. So let's see how all this builds our foundation for what comes next. We now know how to calculate a vector's size using the norm, and we know how to strip that size away entirely to focus purely on direction by turning them into unit vectors of length 1. But that leaves us with a massive cliffhanger. Once two vectors are shrunk to that exact same length of 1, how does an AI actually measure the angle between them to figure out how similar their directions are? Like, how does a computer mathematically understand that the directions of king and queen are close to each other? Well, that is a fascinating process called cosine similarity, and it will completely change how you view search engines and language models. I hope this sparked your curiosity, and I absolutely can't wait to explore that next step with you soon. Keep learning, and we'll see you next time.